The blue marble. Have you ever wondered why life exists on Earth, but not on other planets in the solar system? Earth is the third planet from the Sun. If it were closer to the Sun, it would be too hot to support animal or plant life. If Earth were farther away, it would be too cold. Instead, Earth contains the perfect conditions to support a variety of climates and habitats that make Earth's plant and animal life possible. Imperfect sphere. Earth is the fifth largest planet in the solar system. It looks like a ball, but its shape is not a perfect sphere. Instead, it bulges at the equator. If you wrapped a tape measure around the equator, it would measure about 25,000 miles, 40,000 kilometers around. It would be roughly 8,000 miles, 13,000 kilometers in diameter or across. What if you measured Earth's diameter between the North and South poles? That number would be 26 miles, 42 kilometers shorter. A trip around the Sun. Like other planets in our solar system, Earth orbits the Sun. Earth's orbit is not a perfect circle. It is an ellipse. Scientists estimate that Earth is an average of 93 million miles, 150 million kilometers from the Sun. It takes 365 days and 6 hours to complete one revolution. An extra day is added in February every 4 years to make up for those extra 6 hours. Years with the extra day are called leap years. Spinning like a top. While orbiting, Earth spins like a top on an invisible axis. That axis extends through the North and South poles. This rotation creates days on the planet. Areas facing the Sun receive daylight. Those facing away experience night. One day on Earth lasts 24 hours. Our planet is divided into 24 time zones. This helps keep track of the different phases of light on Earth. See The Big Truth, page 22, for more information on time zones. Earth's axis tilts 23.5 degrees as the planet orbits. This tilt causes the seasons. For 6 months each year, the northern hemisphere tilts toward the Sun. As Earth revolves around to the other side of the Sun, the southern hemisphere tilts toward the Sun. As a result, when it is summer in one hemisphere, it is winter in the other. When it is spring in one hemisphere, it is fall in the other. Above and below. Below us, our planet is composed of 4 main layers. The outer surface is called the crust. Beneath that are the mantle, outer core, and inner core. Circling overhead is a layer of gases that forms our atmosphere. Each layer plays an important part in Earth's ability to sustain life. For example, plants and animals depend on liquid water on Earth's surface to drink. As a gas, water can travel on winds to fall on places around the world as rain, snow, or hail. The crust. Earth's outermost layer includes the continental crust and oceanic crust. The crust and the uppermost layer of the mantle are broken into sections called tectonic plates. The plates rest on top of a more fluid layer of mantle and are constantly moving. Scientists believe Earth's continents were once joined as a single landmass called Pangaea. Over millions of years, the tectonic plates shifted. This caused Pangaea to break into sections. The sections drifted apart and formed the continents we know today. When tectonic plates slide over or past each other, an earthquake can occur. Sometimes the pressure causes shifts in the oceans. If the ocean earthquake is strong enough, waves can develop into a deadly tsunami. The collision or constant pressure of tectonic plates can create mountain ranges. For example, the Himalayan mountains in Asia grow taller each year. Water on Earth circulates constantly through the water or hydrologic cycle. Liquid water on the planet's surface is heated by the sun and turns into a gas. This gas, called water vapor, rises into the atmosphere. It gathers into clouds and falls back to the ground as precipitation, such as rain or snow. It collects in bodies of water or soaks into the soil. Then it starts the process over again. The mantle. Earth's mantle is a semi-solid and movable layer of rock. It is composed of silicon, oxygen, iron, magnesium, and aluminum. Sometimes this substance rises through the crust above. It surfaces as a volcanic eruption of molten rock. Scientists believe the mantle is about 1,860 miles, 2,993 kilometers deep. This calculation is an estimate. No one has ever drilled deeper than 1.4 miles, 2.3 kilometers beneath the ocean, or 8 miles, 13 kilometers on land. The core. Earth's core has two layers. The liquid outer core is composed mostly of iron and nickel and is about 1,400 miles, 2,250 kilometers thick. It is constantly flowing. Its movement around the inner core creates Earth's magnetic field. Enormous pressure and radiation keep this layer hot. The inner core is solid iron. It may spin faster than Earth's other layers. The whole core is estimated to be 11,000 degrees Fahrenheit, 6,000 degrees Celsius. A layer of protection. Earth's atmosphere wraps the planet like a blanket of insulation. Its two lowest layers are the troposphere and the stratosphere. More layers of thinner and thinner air are above the stratosphere. The troposphere is about 7 miles, 11 kilometers high. It contains the air we breathe. It is 78% nitrogen, 21% oxygen, and 1% other gases. Nearly all of the weather we experience on Earth occurs in the troposphere. The stratosphere is about 30 miles, 48 kilometers high. It contains less water and more ozone than the troposphere. Ozone blocks harmful rays from the sun. The stratosphere and the layers above it also help protect us from objects in space, such as meteoroids. These objects sometimes threaten to crash into Earth. However, a meteoroid creates friction as it moves rapidly through the atmosphere. This usually causes the object to burn up. Which way is north? A compass needle points to Earth's magnetic North Pole. But did you know that the magnetic North Pole is not located at the geographic North Pole? The magnetic pole drifts about 6 to 25 miles, 10 to 40 kilometers each year. The north and south magnetic poles sometimes switch places. When this happens, Earth's magnetic field temporarily becomes twisted and scrambled. But this has only happened 170 times in the last 80 million years. After the next switch, a compass needle that would have pointed north will point south. The big truth. Dividing time. Earth is divided into 24 standard time zones. Each time zone is 1 hour ahead of the zone to the west of it. For example, say it is 3 a.m. in Anchorage, Alaska. At that same moment, it is 4 a.m. in Los Angeles, California. Most areas have adopted these standard time zones, but there are some exceptions. China crosses 3 standard time zones, but the country decided to have only one time zone. Some regions divide time zones by half hours. Iran, Newfoundland and Canada, and parts of Australia are examples. The moon. Some planets have many moons, others have none. Earth has only one moon. It is located an average of 238,855 miles, 384,400 kilometers from Earth. Earth's moon is a type of satellite. A satellite is an object that orbits another, larger object. Moons are natural satellites. That means they were not made by humans. Using this definition, Earth is a natural satellite of the Sun. A helping hand. Although the Moon is a lifeless rock in space, it provides benefits to our planet. Earth's gravity pulls on the Moon, but the Moon's gravity also pulls on Earth. The Moon's gravity causes Earth's ocean tides. They help circulate water and slow Earth's rotation. Scientists believe the Moon's gravitational pull also helps keep the tilt of Earth's axis stable. This keeps our climate stable. Making the Moon. So where did the Moon come from? Some scientists believe that an object the size of Mars collided with Earth 4.5 billion years ago. The Moon was created from molten debris flung into space by the collision. As a result, the Moon's surface contains elements similar to Earth's crust. The Moon has no atmosphere. Therefore, it is not protected from space debris. Craters form when asteroids, meteoroids, and comets hit its surface. Exploring the Moon. The Soviet Union, which included present-day Russia and nearby countries, launched probes to the Moon in 1959. The first probe, Luna 1, missed its target and orbited the Sun instead. Luna 2 crashed on the Moon 33.5 hours after it launched. Its equipment detected no radiation or magnetic field. The United States launched spacecraft to orbit the Moon in 1966 and 1967. These helped map the Moon's surface. The information was used to plan the first manned missions to the Moon. In July 1969, the Apollo 11 spacecraft landed on the Moon. Astronauts Neil Armstrong and Edwin "Buzz" Aldrin became the first people to walk on the Moon's surface. By 1972, 10 more astronauts had repeated that journey. A total of 842 pounds, 382 kilograms of rocks was collected for study. Exploration did not end there. In 2009, the Lunar Crater Observation and Sensing Satellite, LCROSS, discovered water crystals on the Moon. This water could help support future manned missions there. Center of the universe? Ancient civilizations had many different ideas about Earth. Incan and Mayan people believed that Earth had 4 corners. Ancient Egyptians believed the sky was a flat plate held up by 4 mountains. The ancient Chinese believed the sky was a sphere surrounding a flat land. Early Greeks believed Earth was a cork floating on an ocean. Early astronomers used math and observations to learn about the planet. But many mysteries were not solved until the invention of the telescope. Determining shape. In 350 BCE, Greek philosopher Aristotle observed that objects always fell to the ground. This was true no matter where in his travels he dropped them. He also noticed that when ships sail over the horizon, their masts disappear last. He observed that Earth casts a round shadow on the Moon during a lunar eclipse. These and other observations supported the idea that Earth is a sphere. Objects fall toward its center. Imagining the universe. Greek astronomer Claudius Ptolemy drew a map of the solar system in 150 CE. His illustrations placed Earth at the center of the universe. Ptolemy argued that the Sun, Moon, Mercury, Venus, Mars, Jupiter, and Saturn orbited Earth. This was a common idea at the time. Aristotle had supported it 400 years earlier. Ptolemy also created a list of 1,000 stars. Those stars were believed to orbit Earth outside the orbit of Saturn. Ptolemy's theories remained popular for another 1,400 years. Then, in the early 1500s, Polish astronomer Nicholas Copernicus published a book showing the Sun at the center of the universe. This new model better explained the behavior of the planets. However, the Copernican theory conflicted with the teachings of the Catholic Church. The Church was very powerful at the time. and banned Copernicus's book. In 1609, Italian physicist Galileo Galilei was shown a spyglass. The spyglass or telescope made faraway objects appear closer. Galileo improved the design and was able to observe distant planets, moons, and other details for the first time. Galileo published his findings, stating that Copernicus's theories were correct. This and other ideas got him into trouble. In 1633, he was put on trial for disobeying the church. The court sentenced him to life under house arrest. Mission Earth. Technology has come a long way since the days of ancient astronomy. Satellites create detailed images of Earth from space. Probes deep inside the Earth and in the ocean monitor the health of the planet. Global Positioning System (GPS) satellites allow us to navigate the planet without having to study the stars. Now scientists can spot problems and react quickly to natural disasters. This helps reduce the devastation the events could cause. The undiscovered deep. Oceans are one of Earth's most abundant resources, but only 5% of the ocean floor has been explored. That is changing. The National Oceanic and Atmospheric Administration is studying deep water canyons off the coast of Virginia. There, they use remote-operated vehicles, ROVs, and sonar. Woods Hole Oceanographic Institution uses a human-occupied vehicle and other underwater machines to explore and map even deeper waters. These missions help explain Earth's geologic processes. To the center of the Earth. The exact nature of Earth's mantle is still unknown. To solve this mystery, scientists are hoping to drill directly into the mantle and take samples. Geologists plan to drill through a section of the Pacific Ocean floor, estimated to be less than 4 miles, 6.4 kilometers thick. Special drills are being designed to handle the stress of boring through the hard oceanic crust. This $1 billion project is planned to start drilling in 2020. Exploring Earth's mantle through volcanoes. Antarctica's Mount Erebus is one of Earth's most unusual volcanoes. It is largely covered in ice, but it contains a lake of molten hot lava deep inside its crater. Scientists at the McMurdo Station Research Facility analyze the gas and lava produced by Mount Erebus. The data helps explain how and why volcanoes erupt. It can also tell us a lot about the mantle's chemical composition. Destination Space. Human-made satellites also help us study Earth. The Aqua satellite was launched in 2002. Aqua uses microwave technology to see through clouds and monitor Earth's water cycle. For example, water and ice from melting polar caps could shift ocean currents. Weather would change, and Earth's temperatures could plunge. Other satellites look for activity signaling earthquakes, tsunamis, or other natural disasters. Satellites can track storms or changes in Earth's climate. To learn how things work in a weightless environment, world scientists designed the International Space Station, ISS. ISS welcomed its first astronauts on November 2, 2000. Since then, more than 200 scientists and engineers have visited the station. They have conducted more than 400 experiments. As of 2013, ISS completed more than 57,000 orbits around Earth. Exploration continues to expand. People once thought Earth was the center of the universe. What will we discover next? Where on Earth are you? Do you use GPS to navigate? If so, you're receiving information from the 29 GPS satellites orbiting Earth. The U.S. Air Force maintains these satellites. 24 satellites are active. The other 5 are backups. The satellites transmit radio signals to a GPS receiver in your phone or car. Signals from 4 or more satellites are needed to accurately determine your position. Digital maps are built into the receiver. They use the satellite's information to help you navigate.